Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're going to talk about this optional material called partition matrices. So this one's actually pretty easy. We're just going to build off of what we've discussed so far. So feel free to not watch this. Nah, I'm kidding. You can watch this video. I mean, you've clicked on it, right? So partition matrices. When we say partition, you know what? I'm just going to Google it. So when we look up partitions here, partitions. Actually, let's just look at partition. When we hear the word partition, separate areas of government, dividing or being divided into parts, divided into parts, divide into parts, divide, division of an entity into parts. So division of parts. So going back to that, this one's pretty self-explanatory. That just means division of a matrix, right? That's what partition matrices is. We just divide a matrix by into groups. So we're going to do that. We're going to divide a matrix into groups. So for matrices in certain special forms, it is possible to use matrix partitions to efficiently compute the inverse. We have a purpose for partitioning matrices. So for instance, I'm going to say matrix partitions help us compute inverse, compute or find inverse of matrix. So right now we only know two things on how to compute the inverse of a matrix. One is we do reduced row echelon form. So we use Gauss-Jordan elimination to achieve that. The second idea we know is a quick formula, but it's only for 2x2 square matrices. And this is a third way, I think. We'll see. I don't know. So matrix partitions can help us compute for an inverse. So let's try this out. So suppose we have this A, and this A is a matrix that contains these entries, capital A, 1, 1, 0, 1, 2, 8, 0, 2, 1, and 8, 2, 2. So immediately we can see this is a diagonal matrix because we only have entries on the diagonal side. But these entries itself are matrices. So I'm just going to say it. Entries are matrices. These are not numbers. These are matrices. It's a matrix inside a matrix. So let's do this. Where A, 1, 1, is an n by n. Oh, I see what they did here. A1, 1 is n sub 1, n sub 1. So that's a square. A1, 2 is an n sub 2, n sub 2. They might have different, we can say n sub 1 and n sub 2 are different, but for sure we know they are square matrices. And so since they're square, I guess, actually we don't know yet, but we explicitly say here that both A11 and A12 are invertible. Okay? So now what are the zeros here? 0, 1, 2, 0, 2, 1 are zero matrices. So they just have entries of 0, and they have dimensions respectively, n sub 1 by n sub 1, and n sub 2 by n sub 2. So they're also square matrices. Okay. So what is A? What do we call A? A is what we call, it's a diagonal matrix, right? But to be more specific, it's a block diagonal matrix. Because instead of the entries being numbers, they are actually matrices. And so we can kind of categorize them as blocks, if that makes sense. So we're looking at a certain block or a certain matrix inside the bigger matrix that we have. Now to find the inverse, let's do B again. Inverse, oh, bet you can't read what inverse when I wrote it. There we go. It's fine. Inverse of A. So B here is, well, also a bunch of matrices. B11, B12, B21, B22. So say we have that. So these are blocks of B, and they have appropriate dimensions so that AB is defined and can be computed using block multiplication. Okay? So we're going to say here that blocks of B what can we say about the blocks of B? They have appropriate dimensions. Uh-oh. OneNote's not responding again. Ay, ay, ay. Have appropriate dimensions. Okay? So we can say, oops, that the product of these two works, or it's defined. So that means we can compute it. Now we assume that actually computing AB, given that B is the inverse, will give us an identity matrix. And from this, we determine the form required of B that will give us a formula for A to the -1. Okay? So here to start, we're going to write that I is I n1, 0, 1, 2, 0, 2, 1, I n2. Okay? So we say that I n1 is an n1 n sub 1. So these are square matrices, n sub 1, n sub 1, and I n2 is an n sub 2 by n sub 2. I'm kind of skeptical though. Why do they call it n instead of the index 1, 1, or 1, 2? But I think maybe it's because of the number of pivots that they're going to get, which are all ones, right? That's just the number of pivots of an identity matrix. At least we can look at it that way. And we already know what 0, 1, and 0, 2, 1 are. Okay. Now, we know what 0, 1, 2, and 0, 2, 1 are. We just define them above here. There are matrices with zero entries, and they have the same number of dimensions as defined above. So if the product AB is the identity, then we're going to have this type of formula. A11, B11 is 0, 1, 2, B21, which is I and 1. Where did I get that? I multiplied A11 times B11, 0, 1, 2 times B21, and that's equal to the first entry. And we're going to keep doing that again and again, right? Until we get to the last. So it's again just a dot product, but with matrices. So this is, I'm going to say this is tricky without I would just ask a computer to do this myself. Maybe that's why they made it optional. But here I'm just writing what the idea behind this is, because I don't want to, of course I don't want to take forever. And then the rest are zeros here. Okay. So this is, there's going to be 4 equations. If we focus on the first and the fourth equations, okay, I'm just going to write that the first and fourth equations imply, what do they imply? That the inverse, or B11, is actually A inverse 1, 1. How do I know? Well, this first equation, if we solve it, A11, B11 is the identity. And so we just say that this B is the inverse, and that would satisfy that equation, this matrix equation, right? And similarly, for 4, we say that B22 is actually just B inverse, no, A inverse 22. Okay. Now, the second equation reduces to A11, B12 is 0, 1, 2. And since A11 is invertible, B12 is equal to 0, 1, 2. And those were one of the properties that we have. And now a similar argument can be used to show that B21 is equal to 0, 2, 1. Okay, I'm not going to write any of those out anymore. They're not super important, I would say. They're not fundamentally there. These are just things we can build off of. So I'm not gonna make it too complicated. But here we can conclude. So the idea, right, is you want to get the inverse. And so that's just gonna be A inverse, right? Because we've solved it. And then we have 0, 1, 2. And then we have 0, 2, 1. And then we also have A, 2, 2. So here we're just making sort of a formula for finding the inverse. Given that we have these blocks or matrices in the matrix, if that makes sense. And we can actually stretch this out, find an inverse of A. So the original matrix A is going to be, and I think we said that here. Oh yeah, I already said it. Why am I saying it here again? Oh, if we find the inverse. Okay, I'm not going to say that anymore. So we actually get back to, oh, wait a minute. Why? Hmm. Wait, we actually get a different one. What? A is, we have A11, A21, 0, 1, 2, A22. Oh, we could find an inverse formula for a new thing. Okay, right. I'm not gonna do that anymore. Okay, that was a new one. Okay, that was confusing. Yeah, but that's the idea of finding out. So here we just found a formula for A inverse. Okay. And we also use that quick formula to do it. Oh my goodness. Right. So let's try our last example here, just to see how we can apply this partitioning of matrices. Well, here's how we can apply it if matrices are too big. Okay, let's wait for OneNote to respond. And right. Hmm. So suppose we have this A, and goodness me, we have a couple of entries, 2, 3, 1, 2, 0, 3, 4, -1, -4, 3, 0, 0, -2, 0, 0, 0, 0, 9, 7. Then last one, 0, 0, 0, 4, 3. I would just use code to do this. But I'm trying to show how this big of a matrix we can use partitioning to make it easier if we want to do it by hand. So suppose that all of the zeros in the upper right of A suggests that we partition A into blocks. So we're just going to partition them. We're going to say A11 is going to have the matrix, say 2, 3, 3, 4. We could write it like that. Let's look at A12. Uh-oh. Okay. A12 is going to have the 0. So here it's really up to us how we want to partition them. I'm going to partition it this way. But either way, there's not an exact way of partitioning matrices. It's really up to you how you want to do it. As long as you can solve it, obviously. Okay, let's do 1. So we have 1, -1, 2, 4. Oh yeah, also we have to make sure that the diagonal are square matrices. Okay. It's also another thing that we want to keep in mind. So we make sure that A11 and A22 are square matrices. So I could just write the rest of the remaining entries here. Okay, A11 and A22. So the way we cut them out like this. This is A11, A12, A22, A21. And so in other words, we cut them out. Oh my goodness. We cut them out like this. A11, A21, A12, A22. Right? Okay. So after we've partitioned them, now we have our separate matrices to take care of. And so this is luckily a 2 by 2. We can actually apply the formula, right? So we had a formula given here. I think it was one of these. Oh, where was it? Uh-oh. I think I forgot to write out the formula. Given in phi? What formula are we talking about? Oh, we're talking about the... Oh, there was another formula. Oh, shoot. My bad. If we're given a block lower triangular matrix. Yeah, there was a formula for that. I forgot to put it here. I thought it wasn't needed. Anyway, but if we have a block lower, basically a lower triangular matrix, but it's blocks. So we say something like if A is a block lower triangular matrix, so we say A11, A21, A22, 0. This thing here is a lower triangular, but it's a block, so block lower triangular matrix. Then our inverse has the following formula. It's also going to be a 2 by 2. A inverse 11. And then this one's a bit weird, but A inverse 2, 2. A21, which you already have, times A negative 1, 1, 1. Then here we still have this 0, and here we have A 2, 2, negative 1. And so the way we do this is, okay, we have this, right? Now we need to compute for everything we need. So let's compute this matrix here. So that's going to be 1 over 8 minus 9. We multiply it to this matrix here. A 1, 1, 2, 3, and 3, 4. And we're going to get a matrix out of it. We're going to get negative 4, 3, 3, negative 2. And the way to check is, well, if we multiply this matrix by this matrix, it's going to be identity. Okay? Wait, is it? Wait a minute. Oh, no. My bad. If I multiply this guy by this guy. All right, so we have that. Let's compute for the other ones. Let's try a negative 1, 2, 2. So if we compute for that thing, we're going to get what? Negative a half. You guys can compute it for yourselves. These are one of the things I hate doing. Now that I think about it, I don't like computing by hand. It's just annoying. And finally, we compute this guy here. So this times, we already have this one. And we just need this one. Is that what we wrote? Yeah. We already have the inverse, we already have this, so yeah, we just compute what we need, and we're gonna get, holy moly, no, I'm kidding. It's not even that bad. I'm kidding, it's bad. 96, 221, 5 half, 66, 162. Or no, 152. Cool, very nice. Now combining them, Jesus. But combining them, we get something really creepy, and I don't want to look at it, but here it is. The A inverse of that whole thing after partitioning of 4, 3, negative 7 half, negative 96, negative 221. No, not negative, actually. 221. And then we have 3, negative 2, 5 half, 66. And we have negative 1, 5, 2, 0, 0, negative a half, 0, 0, 0, 0, 0, 3, negative 7. No, actually, negative 3 and positive 7. And then we also have 0, 0, 0, 4, negative 9. And there we have it. Phew. So we have two formulas that we can use for more complex block matrices, but those are really partitions. Anyways, I hope you guys enjoyed this video, and I'll see you all next one.